Looking at notes on resistance, we're going to be talking about resistors and how they combine in series, parallel, and in a combination of the two. Now, in your note packet, you should already have see this and have it written out, but just to remind you of some of the basics. Resistance, which is represented by a capital R, is a opposition to the flow of charges, and its units are ohms, which is a capital Greek omega. Current, I, um, usually it's capital I, lowercase I is possible too if you're talking about a current that is going in one direction and then branches off into smaller ones. Sometimes those will be listed as lowercase i's, but in any equation that you're going to see, it's going to be capital I, which is the rate at which charges pass a given point. It sounds a lot like an equation, which it is, that I, the current, is equal to the charge over time. So its units would be coulombs per second, which is known as an ampere, hence an ammeter. And the other big term we're going to be using right now is voltage, which is the electric potential difference. In our notes, we're going to be dropping the delta sign, but keep in mind that this still means the differences. So you're going to need to have 2 points that you're going to measure the difference between. Okay. Now, when resistors are placed in series, they come one right after another. And there's only one way that charges can flow, much like in the World Series or a series in basketball or something like that. You have to play game 2 before you can play game 5. And what we will see in this is that voltage across the resistors will vary with the resistance while the current remains the same throughout. Alternately, when resistors are placed in parallel, there's absolutely multiple paths in which they can flow. I personally like the little finger method where you're going along, and then if you come to a point when your finger's a little individual charge, and if you come to a point where your finger can't go all the ways, that's an indication that we're going to be moving into the possibility of a parallel. So in this parallel arrangement, the current through each branch will vary based on the resistance in that branch, but the defining key, the thing that makes parallel arrangement, is the fact that the voltage in each branch is going to be exactly the same. Now, when we combine resistors, what we're going to do is basically treat it as if we're replacing them with a single resistor, and that single resistance is known as the equivalent resistance. You've got the definition here, and the idea is just that we want to replace all of the resistors in a specific area or in the entire circuit with um, a single resistor that will draw as much current, the same total current from the battery. So what we're going to be doing is talking about how to add resistors in series and parallel. So the standard way of talking about this is that if we're in series and we're just coming one right after each other, if you notice on the screen, you can go from R1 through R3 in the series column, and to get from A to B, you've got to go through each one of those. So in series, it's super easy. Resistances simply add, just boom, boom, boom. Take all the resistors, add them up, you're done. In parallel, what we're going to notice is that the when we get to that A point there, we've got options. Okay. So the charges have options about which way they can go. So the total resistance is not as straightforward as it is in the series. And the inverse of the equivalent resistance would be equal to the sum of the inverses of the resistors in each branch. Okay, that's the formal way. The way that you're going to see it on the equation sheet and the way I prefer to think about it is using that REQ in parallel is equal to the quantity of 1 over R1 plus 1 over R2 plus 1 over R3, et cetera, et cetera. That entire quantity raised to the -1 power. Now, example time. So let's say that we have 3 resistors here, R1, R2, and R3, 10, 33, and 70 ohms respectively. If you look at this, it's pretty obvious that you have to go through all 3 to get from the left to the right. And so these 3 are in series. I personally tend to circle the 3 in series, and then the idea is you can replace it with a single resistance, a single resistor that has the equivalent resistance of all 3. And so since they're in series, we're just going to add them up. So 10 plus 33 plus 70, which comes out to be 113 ohms. And you can check your lower right corner. I'm pretty sure I got that one right. Okay, next up. Over here, if you notice, if we start at the far left-hand side and we move our finger along, we suddenly come to a branch or a like junction. There's a point where there's two different ways we can go. We can either go through the 330 ohm resistor or through the 100 ohm resistor, but our one finger can't go through both and get to the other side in one trip. So these are in parallel. You're going to see me use parentheses kind of for parallel. And I'm going to replace those two resistors with a single resistor with an equivalent resistance of R parallel, which is just 1 over R1 plus 1 over 2, that quantity taken to the negative 1. So plug in my numbers and I get 76.74418, which would round to 76.7 ohms. So when you're looking at this and you're reading through these, you should be able to see that when they're combined in series, what happens to the total resistance? It's greater than each individual resistor. While in parallel, the total resistance is less than the resistance in each individual each individual resistor's resistance. So at this point, what you're going to want to do is work on the guided examples and kind of work through the rest of the packet for our next class.